So now that we've talked about some general aspects of higher order ODEs, now let's talk about how to actually produce some solutions. And here we'll talk about the solutions of the homogeneous ODE with constant coefficients. The main topics that I'll hit are how to solve the second order ODE, and then we'll talk about some properties of the higher order ODEs. And in particular, there may be cases in which we need to do some special things to find all of the n linearly independent solutions for the n order ODE. Okay. Um, you will, after seeing this video and doing the problem sets, I would like you to write this down again. You will be able to solve the case of a homogeneous ODE with constant coefficients of order 2 and higher. So keep that as your main goal as you watch this video. Now, just to make sure we're all on the same page here, remember the general uh, linear ODE could be expressed as the form as the nth derivative of y plus a coefficient p1, which is in general a function of x, times the n minus first derivative of y, summed all the way down to the p n minus 1 coefficient times y prime, the first derivative of y, plus p sub n of x times y is equal to 0, right? So there's no term that's independent of y, so the right-hand side is 0, and the p's are the coefficients. And in the case of constant coefficients, the p's here will be constant. They're independent of x and constant. So let's first talk about second order. And so the general form of the second order homogeneous ODE, again with constant coefficients, is y double prime plus a constant, we'll just call that a1 times y prime, plus a constant a2 times y is equal to 0. So how do we solve this problem? Before we get into that, let's recall the first order case. Say y prime, not p prime, y prime plus a times y is equal to 0. And this you can easily solve now, hopefully, and you should get the solution y is equal to c e to the minus ax. And so you'll notice that the homogeneous case for the first order ODE had a solution that was proportional to had an exponent in the solution. So if this is true for first order, we might hypothesize that exponentials are part of the solution for second and higher order solutions. So let's assume higher order ODEs have exponents in the solution. That's certainly a logical function to try, and let's see what happens. So let's assume that y is equal to e to the lambda x. and where lambda here is just a constant. And if we um, plug this into our equation, we see that y double prime, well, y prime will be lambda, either the lambda x, and lambda double prime will be lambda squared e to, well, e to the lambda x. And so we'll have a1 lambda e to the lambda x plus a2 e to the lambda x, and that's equal to 0. And you can see here that we can divide both sides by e to the lambda x, and we'll get what we call the characteristic equation. So that's lambda squared plus a1 lambda plus a2. And this is the characteristic equation for this second order ODE. And so all we would need to do is to solve for lambda. And oh, I'm sorry, the equation of course has to have an equal sign, and it's equal to 0. And you know how to solve this. You solve the quadratic equation using the quadratic formula. So the way I learned the quadratic formula was something like, well, I'll just say lambda squared, a lambda squared plus b lambda plus c is equal to 0. And the solution is lambda is equal to minus b plus and minus the square root of b squared minus 4ac all over 2a. That's if the coefficients are a, b, and c. The coefficients here are 1, a1, and a2, so that gives the solution for lambda being equal to negative a1 plus and minus the square root of a1 squared minus 4a2 all over 2a. Okay, so we have the solution to a quadratic equation has two roots, a minus a1 over, sorry, over 2, minus a1 over 2 plus the square root of this, or minus a1 over 2 minus the square root of this. And as you'll recall, an n-order ODE has two linearly independent solutions, and for many cases, an n-order ODE has n linearly independent solutions. A second-order ODE has two independent solutions, and in many cases, the two solutions for lambda will give those two solutions. So in general, for this case, the solution is y is equal to c1 e to the lambda 1x plus c2 e to the lambda 2x. And that's the solution to this second order linear ODE. Okay, so now let's look at a specific example. And this is one given by Greenberg on page 96. And that example is y double prime minus y prime minus 6y is equal to 0. So again, we're going to assume a solution that's proportional to e to the lambda x. And when we assume that, we get our characteristic equation. When we substitute this in for each of our y's, we get lambda squared minus lambda minus 6 is equal to 0. And that tells us that lambda is equal to 1 plus and minus the square root of 1 to b squared, which is 1, minus 4 times 6, which is plus 24, all over 2a, which is 2 times 1. Or in other words, that's 1 plus and minus 5 over 2, and that's equal to 3 and minus 2. Those are our two roots for lambda. And that gives the general solution. Again, the general solution encompasses all possible solutions. C1 e to the 3x plus C2 e to the minus 2x. Okay, so that's not too terrible. It's relatively simple. Now let's look at the example that we looked at before. This was the example we looked at the previous video. Oops. And we talked about the solution, but we didn't derive it. So let's just go through and derive the solution. That's y double prime minus 9y is equal to 0. And so that gives the characteristic equation. Again, we assume y of the form e to the lambda x. If we substitute e to the lambda x into here, the second derivative gives us a lambda squared. And then we have 9 times e to the lambda x. And the e to the lambda x's, well, are right here. So we get, and so this, our characteristic equation is lambda squared minus 9. And that gives lambda is equal to plus or minus 3. And so the full solution is y is equal to c1 e to the 3x plus c2 e to the minus 3x. And so that's a great way to write the general solution. But an alternative way, as we talked about before, remember e to the x is related to our hyperbolic functions. And so e to the 3x, for example, is equal to cosh 3x plus sinh 3x. And e to the minus 3x is equal to cosh 3x minus sinh 3x. And if we substitute these into our general solution, we will find that we'll get, we'll just say a1 cosh 3x plus a2 sinh 3x. I'm using different variables for the constants because the constants will change if you write the solution using the hyperbolic functions as opposed to the exponential functions. Now you can show your solutions in either form that you choose. They're both equivalent. But one practical consideration is the initial condition. For example, if your initial condition is at x equals 0, it would be easier or more desirable to use the hyperbolic functions because, as you know, cosh of 0 is 1 and sinh of 0 is 0. So let's look at one more example. Well, I guess this is our example 3 or example 4 in Greenberg, page 98. And the equation is y double prime plus 4y prime plus 7y is equal to 0. And so this gives the characteristic equation. Whenever you see a double prime, you know that's lambda squared. And wherever you a single prime, that's just lambda. So we have 4 lambda. And then when there's no derivative, this term just drops out. So that's 7. So this is our characteristic equation. And the solution is lambda is equal to minus 4 plus and minus the square root of 4 squared, 16, minus 4 times 7, that's 28, all over 2. And this solution is interesting in that it's imaginary. It's minus 2 plus and minus I times the square root of 3. Now the I comes from taking the square root of a negative number, right? 16 minus 28 is minus 12. So when we take the square root of minus 12, we get an I. 12 is the product of 3 times 4. And when we take the square root of 4, we get a 2 in the numerator that cancels with the 2 in the denominator, and we're left with an I times the square root of 3. So let's look at the general solution with this imaginary lambda, and that is C1 e to the minus 2 plus I times the square root of 3 times x plus C2 e to the minus 2 minus I times the square root of 3 times x. And we can collect terms, write this out slightly more simply as y is equal to e to the minus 2x times c1 e to the I square root of 3x plus c2 e to the minus I square root of 3 times x. And so, right, so that's one way to write our general solution. And the imaginary number in the exponent leads to a periodic behavior, right? From Euler's formula, we know that e to the I square root of 3x is equal to cosine square root of 3x plus I sine square root of 3x, and e to the minus I square root of 3x is equal to cosine square root of 3x minus I sine square root of 3x. And so we could write this also as e to the minus 2x times a1 cosine square root of 3x, just to make sure. So the square root of 3x is in the cosine function, plus a2 sine square root of 3x. And these are two equivalent ways of writing the general solution to this problem. So just to recap, in our previous example, when lambda was entirely real, we found that y was an exponential function of x. In this case, when lambda is imaginary, we get an exponential function times an oscillatory behavior of x. So again, we were solving the second order homogeneous ODE with constant coefficients, and we showed that we could have quite a rich range of behaviors given depending on the sign or of lambda, or whether it's real or complex. Okay, so now let's move on to looking at higher order ODEs. So the higher order, the n order ODE, as you'll recall, is the nth derivative of y plus a coefficient that's constant. I'll call that, instead of the p's, for the constant coefficients, we'll use a's. a1 times the n minus 1 derivative of y plus all the subsequent derivatives down to a n minus 1 times the first derivative plus a n times y is equal to 0. And again, if we assume that y is proportional to e to the lambda x, we'll get a characteristic equation that is lambda to the n power plus lambda to the n minus 1 power. These correspond to these parts of the original ODE, and summed all the way down to the lambda power, sorry, this is a1 lambda n minus 1, all the way down to a n minus 1 times lambda plus a n is equals to 0. So this is an n order equation, and lambda has n roots. N roots. And it's possible that the n roots will give the n linearly independent solutions that make up the general solution. That is C1 e to the lambda 1x plus C2 e to the lambda 2x all the way down to Cn e to the nth root of lambda times x. And well, for example, you should see the roots function in MATLAB. It's a very pretty simple function to find the roots of a n order equation. So if you need to, you can use that function. And so this is how we might arrive at the solution for a higher order equation. That is, if the lambda, if the roots are distinct, we get the full solution. And this leads, I guess, to theorem 3.4.1, which states that if we say, let's let lambda 1, lambda 2, all the way up to lambda n be any number, real or complex, I guess we should say any set of numbers real or complex, the set of functions e to the lambda 1x, e to the lambda 2x, all the way out to e to the lambda nx, that set is linearly independent if and only if the lambdas are distinct. That is, if they're different numbers. So if we have an n order ODE and we solve the characteristic equation and we get n roots, and if all the roots are different numbers, then the set of solutions with e to the lambda 1x, e to the lambda 2x, all the way out to lambda e to the nx, this set of functions defines the linearly independent set and thus gives the general solution to the ODE. And that's important. Okay, so let's look at an example in which the roots are not distinct. So let's suppose we have y double prime plus 2y prime plus y is equal to 0. In that case, our characteristic equation, again, whenever we see a double prime, we get a lambda squared. Whenever we see a single prime, we get a lambda multiplied by the coefficient plus, plus 1. That's the coefficient on y. This is the characteristic equation. And this gives lambda is equal to minus 2 plus and minus the square root of 2 squared, 4, minus 4ac, which is 4, all over 2a, which is 2, and that's equal to minus 1 and minus 1. So we have only one number representing two roots. So we would here say that the two roots are identical. So this implies that we have the solution y is equal to c1 e to the minus 1 times x. But remember, we had the theorem, it was way back, well, theorem 3.3.3, and that stated that for a second order ODE, there must be two linearly independent solutions, but we only have one. So what that tells us is that not in all cases will all the linearly independent solutions be exactly of the form of e to the lambda x. So we have to look for other forms. And I'm not going to go through the method of how you do that, but you should see, let's see, example 9 on page 102 for a derivation. It's not really a derivation, it's a well, it's a derivation for, yeah, for the other Li solutions of a second order case. And for this case, it turns out that the general solution is y is equal to c1 e to the minus x plus c2 x e to the minus x. So let's go back and talk about the what to do for the more general case. So first, let's define. Let's give you a definition here. So if root number j, that is lambda j, is found to be a repeated root, and it's repeated k times. In our quadratic equation, we had a repeat root that was repeated 2 times. If we were to have a cubic equation, we might find a root that's repeated 3 times. But in general, if we find a root that has k redundant values, we say this is a root of order k. And we must therefore seek k minus 1 more linearly independent functions to get all the solutions associated with that repeat root, lambda j, right? Okay, right. If a root j is repeated k times, 2 or 3 times, for example, we say this is a root of order k, and we must seek k minus 1 more linearly independent functions, and these are different from e to the lambda jx to get the remaining solutions associated with this particular root. Now let's consider theorem 3.4.2. If lambda j is of order k, that it repeats k times, and that's of the characteristic equation, then the k linearly independent solutions are e to the lambda j k, sorry, x, lambda j x, x e to the lambda j x, x squared e to the lambda j x, all the way up to x to the k minus 1 e to the lambda j x. So these, if the root is not repeated, then we just have this solution. But if it's repeated k times, then we have x, x we multiply by x raised to the various powers to get the remaining k minus 1 solutions. So returning to our last example, lambda here was a repeated root of order 2. So the first root gives us e to the minus, or e to the lambda x, and then our second root, or the first repetition, gives us x to the first power times e to the lambda x. So let's look at one example here. So we have y quadruple prime, yeah, there we go, minus y double prime is equal to 0. So here's a fourth order ODE, and the characteristic equation here is lambda to the fourth minus lambda squared is equal to 0. And that can be described as lambda squared times lambda squared minus 1. And that gives the roots lambda is equal to 0, plus and minus 0, so 0 and 0, and plus and minus 1, so 1 and 1. So we have two repeated roots, and we get the general solution for the repeated root for 1. We get, oh, I'm sorry, we get plus and minus 1. So we only have one repeated root. So in that case, we have a e to the x plus b e to the minus x plus c e to the 0 plus dx e to the 0. Again, we had one repeated root here, and so we have e to the lambda x, and then we have x times e to the lambda x as part of the solution. And of course, that could be written as a e to the x plus b e to the minus x plus dx plus c. And this is our full general solution to this fourth order ODE. So I think that's about it. As much as I should cover in this single video. We've covered a lot of ground on solving second order ODEs as well as higher order ODEs.